Hi class, this is Professor Smith. I'm going to be doing a movie on finding a polynomial of given degree with given zeros, complex zeros. In this example, we're asked to find a polynomial f of x of degree 3 with real coefficients and the following zeros, -3 and -1 plus I. So we know that x equal to -3 is a real root, and then we know that x equal to -1 plus I is a complex root. By the complex root theorem, we know that complex numbers come in pairs. So if you have one complex number, it's always going to have a second, which is its conjugate. To find the conjugate, if you have a complex number x equal to a plus bi, then the conjugate is of the form x equal a minus bi. So if you have 2 plus 3i as a complex number, its conjugate would be 2 minus 2i. If you had -3 minus 5i, then its conjugate would be -3 plus 5i. So we can see that when we're looking at the conjugate, it's just the imaginary part that changes. So here we have a +2 that became a -2 for its conjugate. The -5 became a +5. And notice those are all the imaginary parts, the parts that's multiplied by I. So since we know that x equals -1 plus I is a root, we know that its conjugate is also a root. So -1 minus I. If x equal to -3 is a root, then I also know that if I add a 3 to both sides to that first equation, I'll have x plus 3 equal to 0. I know that x plus 3 is going to be a factor. Similarly, if I rewrite the second equation with 0 on the right by adding a 1 and subtracting an I, leaving me with x plus 1 minus I equal to 0, then I also know that x plus 1 minus I is also a factor of our polynomial. It follows then that when I do the same thing for the conjugate by adding a 1 and adding an I have x plus 1 plus I equal to 0. The left-hand side, again, is also a factor. And when you think about it, if each of these terms, x plus 3, x plus 1 minus I, x plus 1 plus I, all equal to 0, that means when I multiply them all, they should equal 0, and hence, therefore, showing that they are indeed zeros of a polynomial. So what we're going to do is we're going to multiply x plus 3 times x plus 1 minus I times x plus 1 plus I. Let's do the multiplication where we have a little more rooms. Finding a polynomial of given degree with given zeros of complex zeros was helpful for you. So we're going to take x plus 3 times x plus 1 minus I times x plus 1 plus I. I'm going to multiply the two factors that have the complex zeros first. And then I'm going to also observe something that's pretty cool. I notice that I have an x plus 1 as the first two terms in the first factor, and then I also have an x plus 1 as the first two terms of the second factor. When I multiply a difference in a sum, something of the form a minus bi times a plus bi, I know that something cool happens. The middle term, which will result in the minus abi, or bi times a, and then when I multiply the outer terms, a times bi, when I add those up, since I have the opposite of abi plus abi, I'm going to get 0. So it turns out the middle terms will always cancel. And so I only have a times a, which is a squared, and then minus bi times positive bi, which leaves me with minus bi quantity squared, which is equal to a squared minus b squared I squared. Recall from earlier that I squared is equal to negative 1. Therefore, I can rewrite a squared minus b squared I squared as a squared minus b squared times negative 1. And here I have minus b squared times negative 1. That becomes a squared plus b squared. So whenever I'm multiplying a sum or difference times a sum with complex numbers, I know that it's just going to be the first, or the real part, a squared plus b squared. So that means I have here a difference times a sum. I know that this product is just going to be x plus 1 squared plus I squared. Plus 1 squared, sorry. And so then I have x plus 1 times x plus 1 plus 1. So when I multiply that out, I get x squared. Doing the outside, I get 1x. Inside, I get 1x. So when I add them together, I get 2x. And then 1 plus 1 squared is plus 1 plus 1. So it becomes x squared plus 2x plus 2 when I multiply the two complex factors, or the two factors with the complex zeros. So now to get the polynomial, I've got to remember there's also the real part, the x plus 3. So now I'm going to multiply x plus 3 times x squared plus 2x. So x squared plus 2x times x plus 3. So what I can do is I can take the 3 and multiply it by the 2, the 2x, and the x squared. 3 times 2 is 6. 3 times 2x is 6x. And 3 times x squared is 3x squared. All those terms are positive because that's a positive 3 multiplied by positive x squared plus 2x plus 2. Then I can multiply by the x. So now I'm going to multiply the x times 2 times 2x and x squared. So x times 2 is 2x. And notice I'm writing that 2x underneath the x term. X times 2x is 2 times x. Adding the exponents, that gives me 2x squared. And then when I do x times x squared, that's the same as x to the 1 times x squared. Adding the exponents 1 and 2, I have x cubed. Adding like terms, 6 and 2x is 8x. 3x squared and 2x squared is 6x squared, which is positive, and then x cubed. So when this polynomial will have the roots x equal to negative 1 plus I, x equal to negative 1 minus I, and x equal to 3. So therefore our polynomial is f of x equal to x cubed plus 6x squared plus 8x plus 6. So let's review the steps that we did in order to come up with this polynomial. First, we recognize that if you have one complex zero, then its conjugate will also be a complex zero. The next thing we did is we rewrote x equal to that complex zero, a plus bi. We wrote it as x minus a minus bi. We know again that its conjugate will also be a root, a minus bi. So we rewrote that x equal to a minus bi by subtracting an a and adding a bi. So we have x minus a plus bi. And in our other case, we had one real zero. So that would, in that case, it was x equal to some number c. Subtracting c, we would have x minus c. Multiplying all of those would then, again, yes, indeed, be 0. And so therefore, that's why we know x equal to a plus bi, x equal to a minus bi, x equal to c. I know those are going to be complex roots. Then the next thing we did is, why do I have a square there? I don't know why I have a square there. And then the next thing we did is we multiplied. I noticed that this is x minus a. The first two terms and the first factor is x minus a. And the first two terms and the second factor for the conjugate, and that's always going to be the case. So now when I multiply a difference times the sum, those middle terms cancel out. So I'm just going to get x minus a squared minus bi squared times that linear factor x minus c. Bi squared simplified because we know that I squared is equal to 1, negative 1, pardon me. So when I replace that negative 1 for I squared, I get x minus a quantity squared minus b times negative 1 times x minus c. And then I go, oh, wait a moment, I have a negative b and a negative 1, and that's why, sorry, b squared. And that's why I had x minus a squared plus b squared times x minus c. In our case, b was 1. And so when we expand this out and then multiply by x minus c, that'll give us our resulting polynomial. So I hope this video on